In this video, we're going to be talking about the sliding window technique, and we're going to look at a few examples where the technique can be used to make slow and naive solutions just a bit faster. Okay, so first, let's talk about what exactly a sliding window or what the technique behind sliding window is. So generally, the idea behind the sliding window technique is, or problems behind the sliding window, is essentially to slide a subarray that we call a window. And this window can have static or dynamic length. And what we do is we do this, or we basically slide this subarray in a linear fashion from left to right. And we essentially do this over the original array of n elements in order to compute something we want. And generally, we're trying to speed up a solution that runs in O of n squared time, for example, into O of n. Okay, so first, let's look at a very simple example of how a sliding window might look like, where the blue part is our window and the array is our n elements. So in this case, the window might slide something like this, from left to right in a linear fashion. And you can see that it's not running in O of n squared time, for example. It's just running in O of n time. Okay, so let's look at our first example of a static sliding window technique that we might use. So the problem states, given an array of n elements, what is the maximum sum of all subarrays of size k? And once again, a subarray is just a section of the array. So this is like contiguous. So it's, for example, if you had 1, 2, 3, 4, 5, 2, 3, 4 might be a subarray. And we want to find what is the maximum sum out of all the subarrays of size k, and we want to print that out. So if we had, for example, n is equal to 10 and k is equal to 3, and then we had the elements 5, 1, 3, 5, 10, 7, 4, 9, 2, and then 8, then we can see that the maximum sum of all subarrays of size 3 is going to be 22, and that's contained within the elements 5, 10, and then 7. Okay, so let's look at exactly how we might do this. So once again, we have n is equal to 10, and k is equal to 3. In this case, we have these same elements as I showed before. And what we want to do is, for this sliding window technique, in this video, we're not going to be talking about the naive solution. A naive solution might run in O of n times k time. And in that solution, we just need to look at, for each index, right, for each element in the array, let's make a window of size 3 and then find the sum there. But what we want to do is, in the sliding window technique, what we want to do is first find the sum of the first k elements, and then we're going to start sliding our window in a linear fashion. So to do this, maintain 2 pointers for the left and right of our window. And what we're going to do is, when we slide this window 1 index to the right, the element 1 index to the right of our window will be added, and the leftmost, or the last element of our window, will be removed. Okay, so if we see that this is our current sliding window, we can see that we have 5, 1, and then 3. When we move this sliding window to the right by 1, we'll add the 5 on the right, but then we're going to be removing the 5 on the left. Okay, so let's look at exactly how this might happen step by step. So this is our array once again, and we're just going to say this is our first k elements. This is the sum of our first k elements, and we can simply compute this in k time. The sum here would be 9. So what we're going to say is the maximum sum so far is going to be 9. We're going to keep track of a running sum, or running maximum. Then what we're going to do is we're going to slide our window to the right by 1. So we're going to add the 5 on the right, but then subtract the 5 on the left. And the sum, or the maximum, stays 9. Then we're going to move the window over to the right by one more, add the 10, subtract the 1. And we get 18. So now our maximum changes from 9 to 18. Move our window once more. So add the 7, subtract the 3, and then we're going to get a maximum of 22 now. Add the 4, subtract the 5, we get a 21. Add the 9, subtract the 10, we get 20. Add the 2, subtract the 7, we get 15. And then add the 8 and subtract the 4, we get 19. And that's pretty much it. So we're going to see that the maximum of all the subarrays of size k is going to be 22. All right, so let's implement it. Okay, so here I'm in my IDE, and I'm just going to implement this solution now. The way the input is formatted is we have an integer n, which is the number of elements in our array, and then we have an integer k, which is the size of our subarrays. Okay, so first let's handle the input. So we're going to have an integer n, an integer k, and then what we're going to do is we're going to create an array to store all these elements. Like so. From there, we're just going to take in for each element in the array, and we're just going to take in its input. So array I is equal to sc.extend. Okay. From there, what we're going to do is we're going to maintain a sum of the current window. We're going to maintain the left pointer, and we're going to maintain the right pointer as well. From there, while the right pointer is less than k, we want to find what is the sum of the first k elements in our array. So we're just going to say sum plus equals array at position r. And then what we're going to do is once we've added the position at position r to our sum, we can increment it. So you can do something like this, or if you want to make it a little more concise, you can do r++ in here as well. Since we're using the postfix notation of the increment, it's going to use the value of r first, and then it's going to increment it. From there, now that we've had the sum of our first k values, we want to store a maximum. What is the maximum of all the possible sums of subarray size k? So let's actually create a maximum sum, and this is at first going to be equal to the current sum of the first k elements. The reason we want to do this is because we're considering the first k elements now. Next, we're going to consider the next k elements, and then so on. So next, we're going to say while the right pointer is less than n, meaning that the right pointer hasn't finished the entire array yet, we're going to first add the value that's on the right side of r. So that's just going to be arr, r++. And then we're going to subtract the left pointer. So sum minus equals array L minus minus, or sorry, L++. The reason we do L++ is because now our left pointer is moved to the right by 1 as well. Now that we've had the current sum, or calculated the current sum of the subarrays of size k, what we're going to do is we're just going to compare that with the maximum sum. So we can say if the current sum is greater than the maximum sum, then we can say maximum sum is equal to the sum, right? We can update the maximum sum value. Another way we could do this is simply by saying max sum is equal to math.max between the max sum itself and the current sum. And finally from there, system.out.println, the maximum sum. And that's pretty much it. So let's run the code and see if it works. And there we go. We get a correct answer of 22. Okay, cool. Okay, so for the next problem of the sliding window technique, we're going to look at something more advanced that uses data structures to actually help us in sliding this window in a linear fashion. So what we're going to do is look at what the problem is first. So the problem states, given an array of size n and an integer k, what is the smallest value in all or each subarrays of size k. So an example of this might be where n is equal to 11 and k is equal to 3. We might have an array that looks something like this. And what we want to do is for each subarray of size 3, what is the minimum element in that subarray? Okay, so let's kind of get some intuition on how we might do this. So what we're going to do is ask ourselves, how can we do this quicker than O of n times k time? So we can obviously do this in a naive approach, where for each element, loop through k times and find the minimum of the first k elements from that index. A naive solution is very trivial. So what we need to do is we need to put in a little more effort when we insert or remove items from our window in order to get that amortized O of 1 time. So we just need to put in a little more effort, and we're going to look at how we might do this. So what we're going to do is we're going to maintain a window such that the elements are in decreasing order. So what does that mean? Well, it means that the left side of the window is always going to be a large value, and then it's going to slowly get smaller and smaller and smaller from the tail to the head. So that's from the left to the right. What we can do is we can pretty much use a heap of some sort, like a priority queue or something like that, to insert the elements. So if we wanted to insert the element array I, we can do that in log of k time. And if we wanted to take out the biggest element from the array, right, we could do that as well. But in this case, we're inserting an element, array I, in log of k time. Or alternatively, what we can do is use a double-ended queue or a DQ to remove elements from the tail, so the left side of the double-ended queue, that are greater than or equal to array I. And then what we're going to do is we're going to insert array I into the back. So we know that the elements at the back of the array, if array I is less than the values at the back of our array, then we know that those values are never going to be the minimum again, right? Because when we slide that window to the right now, and we continue sliding it to the right, then what's going to happen is those values are never going to be the minimum. The answer will be at least array I in this case. So let's look at exactly what I mean by that, because this might seem a little abstract at first. So this will maintain the order of the window, and the minimum element will be at the head of the sliding window. Okay, so let's look at exactly how we're going to do this. Here we have the double-ended queue with the tail and then the head, and here's the array that I proposed in the example. N is equal to 11, and k is equal to 3 in this case. So first what we're going to do is we're going to scan through the first k elements. So we're going to say 1 is here, and then we have a 9, so we can simply just add that from the tail. And then once again, we want to maintain a decreasing order or non-increasing order, or sorry, a strictly decreasing order of our double-ended queue. So now when we see this 5 here, what's going to happen is it's going to remove all the values from the tail, from the back of the window, that are greater than or equal to this value, because we want to maintain that sorted order. So what we're going to do is remove that 9 and then insert that 5. Then we're going to notice that we're going to have to slide a window to the right. When we slide a window to the right, what we should notice is that the minimum value will be taken away, right? It's going to be taken from the head of the array because of the way it's sliding, right? We can simply do that. We can easily check whether or not it's in the sliding window by storing some kind of pair along with the value of the, along with the value of that index. But we'll look at exactly how we might implement this later on. So we added that 7, and since we added that 7 behind the 5, it's still maintaining that decreasing order. And in this case, the window answer, the minimum in this window would be the head, which is 5. Then we're going to add this 5. And we're going to notice that there's still the 7 there, right? But we want to maintain the decreasing order. So what we're going to do is take away this 7, and we might add the 5, for example. Then we look at this 2 here. And then what we're going to do is, because if we insert the 2 from the tail, it's not maintaining that decreasing order, we're going to remove the 5s and then put in the 2. Then we see this 5 here. We're going to insert into our double-ended queue from the tail. See this 3, remove the 5, put in the 3. We see the 9, so we're just going to put it in. But what we should notice is that the 2 is no longer in our sliding window, so we had to remove that. So now we're going to put in the 9. Then we see this 1 here. So we're going to look at the 1. We're going to remove the 9, remove the 3, and then look at the 1. The reason we remove them is because if there's this 1 here, then in all subsequent sliding windows, in all windows later on, the answer will never be a 3 or a 9. It's always going to be at least a 1 in this case. Then we look at the 4, add the 4, and then that's it. And every step along the way, the answer was the head because we maintained that decreasing order. Okay, so let's implement it. Okay, so I'm here in my IDE, and I'm basically just going to first explain what is the sample input that we're going to have. First, we're going to have an integer n, which is the number of elements that we have in our original array. And then we also have this integer k, which is the size of each of the sub-arrays that we want to look at. So first, let's take an input for those. So integer n, integer k. And then what I'm going to do is I'm going to create a static array up here so that we can access it later. From there, I want to actually initialize the array. And then I want to take an input for each of the values in that array. So array I is equal to sc.nextInt. From there, what I want to do is I actually want to create a method called, for example, sliding window minimum. And in this array, or in this method, sorry, I'm basically going to print out what is the sliding window, or what is the minimum in each of the sliding windows. So first, let's actually create that double-ended queue. And what I'm going to do is I'm just going to loop through all the elements first. And from there, what I want to do is let's assume that we're in the middle of our sliding window. So if we're assuming that we're in the middle of sliding our window, what we want to do first is we want to push all the elements that are not inside of our window. Or we want to take out all the elements that are not in our window. And all the elements that are not in our window are going to be at the head of our double-ended queue. So what we're going to say is while the window is not empty, and window.peak, right, that's going to give you the head is less than I minus k plus 1, right? So essentially, if the index, right, of my element at the front is less than the boundary that I'm looking at, right, the size of my window, then what I want to do is just take it out. So we're just going to say window.pull. And once again, or to be more specific, for our double-ended queue, we're storing the indices. Store the indices of the elements. Because if you have the indices, isn't it just pretty easy to get the values themselves, right? All we have to do is say array I. Okay, so first remove the elements not in window. Then what I want to do is I just want to get all, now that I want to insert this element, I want to insert array I. What I want to do is remove elements from the back, right, that are greater than or equal to this element, because I want to maintain that sorted order. So what I'm going to do is I'm going to say, while the window is not empty, right? And array window.peak last, right? The tail, right, on the left side, I want to see whether or not that element is greater than or equal to the element that I want to insert. And well, if it is, then all we have to do is remove it. So poll last, right? So remove elements to maintain, and we'll say here, maintain decreasing order. And now that we've maintained this decreasing order, the element that we want to have, or at the element that is minimum in this sliding window currently, is going to be the one at the head. But before we look at that, let's actually put that element that we want to insert into our sliding window. So window.offer I. And once again, I'm putting the indices because to get the values, we can simply just do something like this, right? Array I, something like that. And what I'm going to do is, because I'm going through the elements starting from 0, I actually want to print them out as long as the index, right, that I'm looking at is greater than or equal to k minus 1. Because if I don't, then I'm also starting off at 0, 1, 2, and all the elements that are less than k. So I'm going to print out now the head, the value at the head of the double-ended cube. So that's just window.peak. And now if we call this function with n and k as my parameters, we can see that it works perfectly fine. So in this video, you learned about the static sliding window technique.